Hello, everyone. Now I will talk about my ICML paper, Accelerated Policy Gradient for S-Rectangular Robust MDPs with Large State Spaces. I'm the first author, Ziyi Chen, from University of Maryland. Robust MDP is an extension of reinforcement learning. In reinforcement learning at time t, the environment is at state st, and then the agent takes action at based on its own policy pi. Then the environment transitions to the next state st+1 based on the transition kernel p. Finally, the agent receives the cost ct. But this is reinforcement learning. But different from that, in robust MDP, the transition kernel P is not fixed, but the range in the ambiguity set, which is assumed to be a convex and compact set, and also S-rectangular, which means the ambiguity set is decomposed into sets among different starting state S. Then the objective function of a robust MDP is a minimax optimization problem, while the policy pi wants to minimize the value function, but the transition kernel P wants to maximize the value function. There are three mainstream methods to solve robust MDP: value iteration, policy iteration, and policy gradient. Among them, the policy gradient methods are the most practical with advantages. For example, a policy gradient has simple implementation and many successes in real world, and also is scalable to large state and action spaces. So we focus on policy gradient method and want to improve it for S-rectangular robust MDP. Our first improvement is to accelerate in deterministic setting with improved iteration complexity. Then we extend to the stochastic setting for the first time and further extend to the stochastic large state spaces for the first time. So we have proposed three algorithms. All of them are also the first policy gradient methods to solve entropy regularized robust MDP, which is also a very important reinforcement learning problem. Entropy regularized robust MDP actually it extends the robust MDP with the entropy regularizer as shown in the red part. The red part is the entropy regularizer. If the tau coefficient tau is 0, then it reduces to the special case of robust MDP. So why do we want to solve the entropy regularized robust MDP? Because we have proved that if a policy pi can solve entropy regularized robust MDP, then it can also solve robust MDP. Therefore, we focus on solving the robust entropy regularized robust MDP. How to solve it? Well, we leverage the strong duality result, which means the min and max can be switched. So why do we do so? Because after switching, the inner minimum among the policy pi has a unique optimal policy pi. Since it's unique, then based on the Densky's theorem, the outer function f is smooth and differentiable. So we can estimate this gradient to update the transition kernel P in the outer loop. Here, to estimate the gradient, we also have to approximate the optimal policy pi. How to do that? Well, in the inner loop, we approximate the optimal policy pi using the well-known natural policy gradient method. Then we obtain the improved iteration complexity in the deterministic case, where we can access the exact Q function and the exact gradient. Then we extend to the stochastic setting, where we can't have access to the exact Q function, but we have to estimate the Q function by the well-known temporal difference method. And then we estimate the gradient using sample average. And finally, we have obtained the sample complexity result of this stochastic algorithm. Furthermore, we extend to the large state spaces setting. Since the space is very large, then we have to use the linear Q function approximation and then estimate it using the TD method. And we also use a linear transition kernel approximation method. That is to reduce the high dimensional P into the low dimensional parameter Kc. And then we update the Kc using the policy gradient method. The gradient is also estimated by sample average, and we then obtain the same sample complexity result. Thank you. Any questions?